Greg, I think you're live. You can start.
Okay. Well, welcome everyone. 안녕하세요. Welcome to ICSE 2020. This isn't quite the way we imagined doing this 4 years ago when we started preparing for South Korea, and I'm sorry we can't be meeting you in South Korea, and I'm particularly sorry for all of the South Korean friends who've helped put this conference together, but I think we've managed to turn it around with the help of Krista Lopes doing virtualization to a conference that hopefully you'll find fulfilling in other ways. So what we're going to do at this moment is I'm going to say a little bit about the structure of the conference, and then the program chair and Duhan Bae, my co-chair. I didn't say I'm Greg Rothermel, general co-chair, and Duhan Bae, my counterpart, will have a few words, and then I'll introduce our program co-chairs, and they'll say a few things, and then Krista Lopes will come on and talk a little bit about the virtualization, and then we will get to the main event, Nancy Leveson talking about software safety. So everyone wants to know the numbers. As of this morning, we had 1,434 main conference registrants and 1,847 total registrants. A bunch of people attended events earlier last week. That does set a new record above last year's in terms of total registrations and main conference registrants. The distribution of people around countries is not much different than it usually is, with the exception of a much larger South Korean contingent, maybe 3 to 5 times larger than normal. So we're glad you're with us. I wanted to show you this. You'll see why in a minute. If you look at the larger regions that people are in, North and South America account for 510, Asia and Oceania 486, Europe and Africa 438. So we're pretty much distributed around the globe. So when we decided to go virtual, the big first question was how to do it. And it seemed like to pick a single monolithic block of time was going to be useful to only 2/3 of the world and leave out 1/3 of the people who come to ICSE. And so we hit upon another scheme that was first suggested by Krista, and that was to use what's called time bands. So I'll spend a couple of minutes on this slide because it's important. It shows up, it's available off of the main page, and it's available in Clouder, and it kind of gives a roadmap to the whole conference. But what I want to point out is there's this notion of time bands. And you'll see on the left, Pacific time band, Indian time band, Atlantic time band. They're named after the oceans. And they're 3-hour blocks of time. Time here is in UTC on this scale, 3 hours blocks of time in which 2/3 of the people in the world should be able to participate without staying up all night. For instance, the Pacific time band, people on either side of the Pacific, the Americas, East Asia and Oceania, can get together as we are doing right now. And it's afternoon and evening in the Americas, and it's morning in the Koreas. People in Europe are probably in bed, but things are going to be recorded so that they can watch them at a later time. The Indian time band is one in which people in East Asia and Oceania can participate with Europeans and people from the African continent. And the Atlantic time band is one where people from Europe and Africa can participate with people from the Americas. Within each of these time bands, then, we've broken them into 3 hours. And in each of the time bands, the first 2 hours are devoted to things you're used to seeing at ICSE's, plenary sessions, parallel sessions with talks, technical briefings, and things like that. The third hour, well, we're calling it just the third hour, sometimes the Zoom hour, but the third hour has smaller events that are more interactive. So after Nancy's keynote, students meeting students, students can go here, and I believe they're going to be playing games. And John Whittle will be holding an Ask Me Anything session. And you can see that there's other things on tap as we go down the week here for posters and demos and such. So those are the third hours. The last thing I'll point out is there's this one weird band of time that we called the almost all band from 1330 to 1430 UTC, where almost everyone in the world can participate with a little bit of pain. I think the West Coast is 6:30 a.m. and I think it's kind of late in Korea. And the only people who are kind of left out are, forgive us, Oceania and New Zealand, Australia, because it's after midnight for you. But pretty much most of the world can come to these things. So we got the town hall meeting and the Rose Festival slotted in there. So very important. I've listed all the times in UTC here, and you've got to translate those to your times, or you'll miss events. And this is a really tricky thing. You know, the sun crosses the date line, and a day begins in Korea and East Asia. And while that day's beginning, it's still nighttime the day before in the Americas. And this opening session here, as you all know, if you're in the Americas right now, is not on July 7 for you, it's on July 6. So for example, this plenary session is occurring at midnight UTC, 9 a.m. Korean time, 8 a.m. Beijing time, 2 in the morning Paris time, 2100 on July 6 in Brazil, 2000 on July 6 in New York, 1700 on July 6 in Seattle. So keep that in mind as you're attending things if you're in the Americas. On the ICSE website, the detailed schedule provides a way to change the time, and I'm going to see if I can show you that. Well, no, I'm not going to be able to do that right now. But if you go to the program time PC, but it lets you change to your own time zone, and then the dates and the times will change to indicate what the times are for you. You'll also find a counter that's counting down to the beginning of the next time band on the top of the ICSE web page. So this is part of a much larger set of events. We've had a bunch of co-located events already, 7 co-located events and some 15 or so workshops in the week before. The pink shows those. And after we're done here, we're in the middle, of course, there are a few more events, a couple more co-located events and workshops. So you should feel free to register for and attend those if they're of interest. Now I want to talk a little bit about some of the program elements. We have 4 keynotes. The plenary keynote today, as you know, is Nancy Leveson talking about software safety. The plenary keynote tomorrow, I want to make particularly note of, is by Chanmo Park. Chanmo is the former chancellor of Pohang University of Science and Technology. That's in South Korea, but he's also the recently prior chancellor of Pyongyang University of Science and Technology. And for those of you who don't know, that's in North Korea. And so he has information on ICT manpower development and software technology in North Korea that you might not otherwise get to hear about. So that should be an interesting keynote. We have Peter O'Hearn giving the 3rd keynote, Formal Reasoning in the Hacker Way, and the Software Engineering and Society keynote, Andreas Stefik, It's Time We Made Software Development Accessible to People with Disabilities. So we also have 5 technical briefings scattered around the schedule in different time bands. So you can access some directly and some will be available recorded. I won't go through these in detail, but you can find information on each of these on the web pages. We have an awards plenary on, I believe it's Friday, and 3 awards to give their Harlan Mills Award, Outstanding Research Award, and Most Influential Paper Award from ICSE 2010. Each of these groups will give a talk about what they're getting the award for in that session. In that almost all time band, there's the SIGSOFT Town Hall. That's where they'll update, you get an update on activities of IEEE TCSE, ACM SIGSOFT, and so forth, and the Rose Festival, where you can celebrate open science and software engineering. The 3rd hour events I talked about briefly, but there's a whole bunch of different types, posters and demos, where you can go and see them individually and talk with the people who are doing them. Birds of Feather sessions, Ask Me Anything sessions. There's a couple of cultural exchange sessions where people will be talking about things in their culture. Students meeting students, where students get together, I think, to play games for the most part. We got the student research competition presentations and a couple of sponsor events where sponsors are in Zoom rooms and able to talk to people, such as probably students who are interested in their companies. We do have a social event. It's Sam Aaron. He's a force in coding, live coding, in coding music. And his event is called Live Coding Choose Your Own Adventure. It's about 17 hours from now. And last, these things are put together by a huge number of people, and I want to acknowledge that. There's 70 organizing committee members. We had to put in a virtualization team about 3 months ago. There were 12 people on that. 67 student volunteers are helping with the sessions. 479 main conference committee members help select papers and things like that. And then in the co-located events and workshops, over 600 more people. So over 1,000 people took part in putting this thing together over the last 4 years, and particularly the last 3 months where we changed directions. And I just wanted to shout out to the organizing committee. If we were doing this live, I'd have them stand up and ask you to applaud for them. That won't quite work, but applaud for them in your minds, please. And maybe they can tell you're doing that, or if you know any of them, send them an email and thank them for what they did afterward. That would be great. Oh, look at that. Thank you. And now let me turn the floor over to Duhan Bey, my general co-chair.
Thank you, Greg. I am Duhan Bey, the general co-chair of ICSI 2020. Once again, I have to say this. It is very unfortunate that we won't be able to hold ICSI 2020 physically in Seoul. I hope we have another chance in future. However, not everything is virtualized. We have small-scale physical events here. One is that one of our keynote speakers, Professor Chanmo Park, is going to give us a talk here physically, which will be live streamed to you on Wednesday. Also, we have 2 local physical events on software safety and software engineering practice in Korean industry. As you can see them through pictures here, as Korean ground team members who are making these virtual as well as physical events happen in South Korea. Thank you for them. Thank you all. This year, we also have the 16 sponsors, as you can see here. You can meet them at the virtual booth as well. Okay, I'd like to thank those sponsors of ICSI 2020 for their generous sponsorship. Now, let me introduce you to PC co-chairs, Darko and Jane.
Hello, my name is Jane Cleland Wong, and I'm Program Co-Chair for ICSI this year with Darko Marino. So we want to tell you a little bit about some of the ways in which we put together the program. If we could go to the next slide, please, Greg. Thank you. So this year, as you can see, we received 617 submissions, which is a record for ICSI so far. And of these 617 submissions, we accepted 129 of them for an acceptance rate of about 21%, which is in line with the previous years. So it's traditional for the program chairs to tell everyone quite a lot about how the program was formed, but because we're doing this online this year, we're going to give a very brief summary and just highlight a few of the things that we think are particularly important. So we had a program committee of 111 people and a program board of 37 people. The program committee members reviewed papers and engaged in discussions and decisions. The program board members did the same thing, except they led the discussions. This is probably the last year that ICSI is going to have a program board. As our whole decision-making and review process has moved online, it's been becoming less important to differentiate these roles. So I know some of you are probably interested. Actually, could we go back one, Greg, please? Thank you. I know some of you are interested in how we formulated the committee. And we were first and foremost looking for diversity of gender, expertise in different areas, geographical representation. We wanted both senior and junior members of the community, and we also wanted people from both academia and industry. So we also needed to expand our committee, seeing as we had so many papers submitted. So this year, SIGSOFT had asked people to self-nominate. We looked in the database that was derived from that. We looked at the proceedings from previous years, and we looked for people who had a track record of ICSI publications, especially people who had never served on the PC before. So that led us to our current PC. You can see at the bottom, as I mentioned, we received 617 submissions. Of these, we desk rejected 15 in the early phases, primarily for reasons of being off topic, for being significantly formatted differently from the required format. And finally, unfortunately, for violating double-blind review requirements. So please be careful about that in your submissions next year. The program committee and the program board evaluated the papers based on their soundness, their significance, their novelty, verifiability, and their presentation. And every paper received at least 3 reviews. We had a very, very vibrant discussion phase where people discussed the papers, leading to over 9,000 comments, an average of 15.3 comments per paper. And this ultimately led to accepting 123 papers with 6 conditional accepts, which ultimately were all accepted, leading to our acceptance rate of 129 papers. And so now I want to just highlight a couple of things about the submissions. In this graph, you can see the blue bars represent the numbers of papers submitted by topic. For those of you who submitted papers, you'll know that when you submit your papers, you can tag them with a number of topics, and we have 51 different topics. The green bars represent the number of papers that were accepted, and the red diamonds represent the actual acceptance rate. So I'm not going to talk about this in depth. You can go and look at these slides afterwards. And if you have any specific questions, you can send a message to Darko or I on Slack. But we thought it was a little bit interesting to point out on the left-hand side, you can see that still very popular topics for ICSE are empirical software engineering, testing, program analysis, software engineering, and maintenance, to just name a few. And an up and rising star, which seems to be rapidly gaining ground every year, if you go back and look at the charts from last year, is AI and software engineering. So this is something for us to look out for. So now I'm going to hand over to my co-chair, Darko, to tell you a little bit more.
Okay. Thank you, Jane. So this was some information about the submissions. Here is about the authors region. Again, we see this representation. We have about 1/3 of the people from Asia Pacific, 1/3 from Europe, and 1/3 from North America. Some more coming from all over the world. We really wanted to make this a global conference. Here's some more information about the review process. We ran this survey where we asked the authors what they think. Overall, they were satisfied. As usual, people had papers accepted, were more satisfied with the reviews than people had papers rejected. Again, the statistics will be available for later for discussion. We don't want this opening to be as long as it would be in a physical conference. Here is some information. It's important for double-blind. ICSE was running a 3-year experiment to determine whether to remain double-blind. The overwhelming majority of authors wanted to remain like that, so probably from now on, ICSE will be double-blind. In terms of who submits, this is also quite interesting to see that our community is quite robust. We have students, postdocs, professors at all ranks and level, so have some representation from industry and hopefully could get even more industry. It's also great to see a lot of people who were first time submitting, and we have a lot of first time attendees, so special welcome to them. Here is the list of people who have helped. We have had a very large PC and PB, almost 150 people plus external reviewers. Thanks a lot to them. Greg said in a physical conference, you would ask them to stand up, but it's all virtual. They can still stand up to exercise. So some of them have gone above and beyond. So we are recognizing a number of reviewers, 16 distinguished reviewers and 13 reliable rapid response reviewers. So special thanks to them. We've also selected a number of distinguished paper awards. So congratulations to all the authors. Here is the list. We have 10 of these papers. More about this you will hear in the award ceremony that will help in Thursday in the Atlantic time band. And I want to do this, the special thanks from the PC chairs. We really had hundreds of people who have helped Jane and me, who have saved us countless hours. But there are 2 people who stand out because they saved us hundreds of hours. Michael Vierhauser, he was our submissions chair. He helped us to start the conference, to set up everything. And then Shang Jushi, who was in our scheduling team and really helped us to put the whole program online and get all of those things done. So special thanks to them. And now I will be turning over to Krista to tell you how we'll run the conference online.
Hello, everyone. I would like to give you just a little overview. You probably are watching this on Clouder, which is this platform that we have developed almost on purpose for ICSI. I just want to give everybody sort of a directions about what to do in case it's not obvious. And I'm sure there are some not obvious things in here, but one thing that you may want to do during the third hour is to visit the exhibit hall. This is where all the live program is. And things like, for example, the posters or the SRC posters, the student research competition, the students have all uploaded their images onto this area of Clouder. When you go inside into one of these posters, you will see not just a bigger version of the poster, but you also get a chat window that you can use to leave messages to the author of this paper. And so you can have sort of an asynchronous or asynchronous conversation with the author. And at the specific times in the program when there is the official poster session, the authors, I would ask, please be here to on the video. And I'm not going to click join the video because my camera is being used on Slacker, on Zoom, I'm sorry. And so I would ask both the poster authors to be here at the designated times in the program, waiting for people to come and join them in the video so that they can explain their posters. This is particularly important for the student research competition posters because they have, judges are coming in to talk to them, but it should also be true for all the other posters and demos of the conference, that they're all having this form of people coming to visit at those designated third hour of all the time bands. So that's one thing that I wanted to point people to. Another thing that I want to point people to is in the video chat lobby, which is sort of a big parking lot right now. But one thing that you can do here is to start, ad hoc video chat conferences with whoever you want. So if you just see somebody here and you want to say hi or change some information. So for example, tomorrow we have scheduled already a meeting here to talk about the award session. So feel free to just start a voice chat here, a video chat here with whoever you want. And this is a place to basically hang out and meet people face to face. So that is what you probably all have already seen your way through the sessions and the live sessions in particular. I want to point out that in this area of the app, there is always happening now. It always says the things that are happening now, as it says in the title. So as time passes, the things that are upcoming are going to move up to happening now, and you can then enter. So for example, in the third hour today, you have the students meeting students and the Ask Me Anythings, and they're happening in a room called Café Royal. And so they will move up here and you can just go and join them. So that's one thing that I want to put out. So keep in mind the live sessions is important. And also when you wake up the next day and you want to watch the previous sessions, you go here to the past sessions and you will see what happened before. So that this is sort of what I wanted to just point out. Feel free to explore everything and try out new things. I want to give, however, a huge thanks to the entire virtualization team. It's not just 12 people. 12 people are the team leaders. So there's 12 people who have sort of managed local teams that are regional. So we have a team in Korea, we have a team here in California, we have a team in Europe that happens to be distributed in the Netherlands and Spain. And we have an additional team in China who is streaming these live sessions to China because the Chinese cannot access YouTube. So this is a huge production. There's about, last time I counted, about 30 people plus another 30 people in China. So it's really amazing, and they're all doing a great job. And this would not be possible without them. Basically, they're bringing you ICSI this time. And I also want to point out that Clowder has been developed very quickly by a very small team that's basically led by Jonathan Bell and myself. I've been coding too, and Benjamin Pierce, who's also been kind of getting into the coding part. And so it is an open source platform. We welcome, people helping out building this out, because we plan to use it for other virtual conferences in the, this year and probably the next. So I hope you enjoy. All bugs are my fault, and all the credit goes to everybody who's putting this virtual conference together. Thank you.
Thank you. Now I'd like to introduce our keynote speaker. I'm pleased to introduce Nancy Leveson. She's the professor of aeronautics and astronautics and professor of engineering systems at MIT, a member of the National Academy of Engineering, a recipient of the ACM Allen Newell Award, the AIAA Information Systems Award, the ACM SIGSOFT Outstanding Research Award. She's well known for her research on software safety and widely credited with playing a foundational role in that area. She's published over 200 research papers, along with extremely influential books on the topic. So I'm very pleased to have with us Nancy Leveson.
There. Is it showing right, Greg?
Yes, it's right, Nancy.
Okay, great. All right, so I'm going to talk, instead of giving you a technical talk about a specific technology or technique that we invented, I want to talk about the problem in general, because we aren't making a lot of progress. And part of the problem is that people are trying to solve the wrong problem. So the first thing we've got to understand is what's the problem we need to solve. So, I love this quote. It's never what we don't know that stops us. It's what we do know that just ain't so. And that's what I'm going to spend a lot of time on. So part of this is, and first of all, I want to start by defining safety. The way I define it, which is a very general definition. An accident, a mishap, a loss, they're all the same thing. And they're any undesired and unplanned event that results in some kind of loss that somebody cares about. For example, loss of human life or injury, property damage, environmental pollution, mission loss, negative business impact, the damaged reputation, product launch delays, legal entanglements. This can be used for everything beyond, and things that are way beyond what people think of as safety. It also, you'll notice there's nothing that says anything about whether it was intentional or non-intentional. So it will also include cybersecurity and security issues. Now, the first thing to understand is there are certain things called system goals, which are the things we're building the system for. But there's also constraints, which are limits on how we can achieve those goals. So our goal in building a power plant or a chemical plant is to produce chemicals. The constraints are constraints on how we can achieve that goal, how we can pollute, how we can produce chemicals. For example, there may be limits on how pollution of the surrounding area. And just a very simple definition, safety is just the absence of losses. People make it really complicated and do all kinds of other things, which gets all kinds of value systems and all kinds of things that we really shouldn't be dealing with in engineering. It's safe if we don't have losses. So safety is all about hazards. If you're not talking about hazards, then you're not talking about safety. Safety engineering is about hazards, and we'll go more into that. But what's a hazard? A hazard is a system state or some set of conditions that together with some particular set of worst case environmental conditions will lead to an accident. So examples are release of nuclear materials, friendly fire. That means firing on your firing weapons at your own troops or your allies. Loss of control of an aircraft. Violation of a minimum separation between autos and planes. Now, the first thing, and I realize that I'm as guilty as anyone, is that we really shouldn't be using the term software safety. Software is not unsafe. It can contribute to a hazard, but it doesn't explode, it doesn't catch on fire, it doesn't involve toxic materials, etc. So software by itself is just an abstraction. It is not unsafe. It can only have any contribute to a hazard if there's a hazard in a physical system that the software is controlling. And we'll talk more about that too. If it's not about hazards, it's not about safety. So here's just a quick overview of what system safety is. System safety engineering. It's a planned, disciplined, systematic approach to preventing or reducing accidents throughout the life cycle of a system. The primary concern is the management of hazards. So hazards need to be identified, evaluated, eliminated, or controlled through various kinds of analysis techniques, through design techniques, and through management. And hazard analysis and control is a continuous iterative process throughout system development and also through the use of the system. You can't stop because the world changes, system changes, and you can't stop worrying about safety just because you've delivered a system. Now, how did I get into this whole thing? It was a little weird. I graduated with my PhD in computer science from UCLA, and I went to my first teaching assignment, which was at the University of California, Irvine, and I was kind of bummed out. My dissertation had been plagiarized. I couldn't publish it. I didn't know what I really wanted to do. So I got a call. I was sort of contemplating all this, and I got a call within my first week there from someone at what was then Hughes Ground Systems. And they said they were making this torpedo. And you can see pictures of this torpedo. This was 1980. And at that time, this was a very sophisticated torpedo, and that had something like 15 microprocessors on it. Before then, people have been pretty much afraid to put computers and software into weapon systems. So this was near the beginning, and they were really concerned. And they said they weren't so concerned that the torpedo would miss the other guy, but they were concerned it would turn around 180 degrees and hit them. And so they said they thought this was a software safety problem. And I said, well, it sounds like software reliability, but that's not what I do. I got my degree in formal semantics of programming languages. I do all this beautiful math. I don't know anything about real things like torpedoes. And they said, well, we have some money. So I said, well, let me put Professor Leveson on the phone. She's the software safety expert here. So they knew I didn't really know anything what I was doing, but they were pretty desperate because they'd already called everyone and couldn't get anyone to answer them else. So I became, so they taught me safety engineering. I don't think I helped them, but I learned a lot. And after it was finished, they came back and they called me and they said, Nancy, are you interested in what happened? And I said, well, sure. And they said, well, we took it out to the torpedo proving grounds and we fired the torpedo. And every time we fired it, it came out of the torpedo tube. You can see that up in the top right. Comes out of the torpedo tube. It turned itself off. It went down to the bottom and it just sort of lay there. And I said, well, it's safe. And they said, well, the Navy doesn't want to pay for this safe torpedo. So I said, well, what did you do about this? By this time, I was out of out of here. And they said, well, one by one, we took off safety devices until it was safe enough and reliable enough. And that was the first time it really hit me, that safety and reliability not only were different, but they were sometimes even conflicting. Making it safer made it less reliable, making it more reliable could make it less safe. And so I had just assumed these were the same thing, because in computer science, reliability is the only thing we've ever had to worry about, because computers have been unreliable since the very beginning, but there's nothing unsafe about software. It's just an abstraction. So I thought, well, I'll spend 6 months. Still didn't know what I wanted to do with my life. And so I said, I'll spend 6 months more working on this problem, solve it for them, and then go on with something else. And it's now been 40 years, but I think I finally have solved the problem. So that's what I want to tell you about, is what I've learned in that 40 years. Now, this is my favorite cartoon. It's still hungry, and I've been stuffing worms into it all day. The problem is we all mean well. The birds were trying to solve a problem. It's just that they were solving the wrong problem. And this is exactly what happens with software and safety, is we're solving the wrong problem, and we hope we're solving the problem of safety, and we aren't. So we've got to stop stuffing worms into the baby and instead figure out what is and understand the problem we're trying to solve. And that's the way we'll make progress. So here's a diagram. Sorry, it's a little busy, but we all talk about cyber physical systems. It really should be cyber human physical systems. And there's a cyber part on the top, and the human part, but the physical system is the controlled process on the bottom. The controlled process is the car, the plane, the spacecraft, the train, whatever. And above that, we have a human controller, which may be controlling a computer controller, which is providing control signals to an actuator, which actually sends those control actions and changes state of the controlled process. And then there's feedback from the controlled process back through sensors back to the human controller and the computer controller. Now, the hazard is only in the controlled process. The other part doesn't have hazards. It's not unsafe. It's the controlled process that we worry about. So software is not unsafe. The control signals it generates can be unsafe or result in a hazard in the physical process. The other thing is virtually all software-related accidents have resulted from unsafe requirements. Not software design errors, not software implementation errors. They're almost virtually all, and I know hundreds of them I've come across in the last 40 years. They all stem from requirements. So let me show you some examples. But first, let me tell you that the state of safety engineering is pretty bad, frankly. The problem is that almost all the techniques that are used, you may not have heard of these, but fault trees, familiar failure modes and effects analysis, hazard operational analysis, HAZOP, event tree analysis, all these other things are all at least 50 to 65 years old. And they were all developed before we had computers controlling these systems. We had computers, but they were not put in control of critical systems. And that changed around in the late 70s, 1980. And all of a sudden we started introducing computer control. There was exponential increases in complexity, lots of new technology and changes in the human roles in systems, extreme changes. So the problem is that these old techniques were all built on the assumption that, which was true then, the accidents were caused by component failures. And the problem is today, that's no longer true. Accidents are not caused necessarily by component failures. So I'm going to show you a whole bunch of examples of this. Oh, it's only a random failure, sir. It will never happen again. All right, here's a real example, hidden, somewhat hidden. So I can't give you the real details. But there were some Navy aircraft that were ferrying some missiles, moving some missiles from one location to another. And they moved them by putting them on the wings of the aircraft, just like they would be flown in a real mission. And one pilot was told that he should execute a test since he was just sitting there not doing much, and he might as well spend his time productively. And by aiming at the aircraft in front of him, at his friend in front of him, and firing a dummy missile. Now, the problem is that nobody knew that this was so-called smart software and was designed to substitute a different missile if the one that was commanded to be fired wasn't in a good position. In this case, there was an antenna between the dummy missile and the target. So the software decided to fire a live missile that was located in a better position instead. Of course, the guy in front who wondered why his friend was firing missiles at him, and everybody was sort of appalled. In case you're worried about the pilot, he was an excellent pilot. He was able to evade the missile. So he was not shot down. But you know what happened. As soon as he landed, somebody said, how did he get away from that missile? We've got to fix that missile. Here's another example. But one of the things, please notice here, is nothing failed. Everything worked. Each component, including the pilot, did exactly what it was designed to do. The problem was in the interactions among the components. Nobody had understood the whole system and how it would all work together. Here's another one. This is the Mars Polar Lander. You have to slow down the software to land safely. It comes in very fast to the planet. It was using the Martian, it uses the Martian atmosphere. This had the parachutes instead of the airbags, and some descent engines. And the descent engines are like reverse thrusters on a plane. They provide thrust against the direction that the spacecraft is going in order to slow it down. And those descent engines are controlled by software. Now, the software has to know that the spacecraft has landed, because if it lands and it doesn't cut off the engines, this thing will shoot up and then fall down again and be destroyed. So there's some very sensitive sensors on the landing legs. And the software engineers were told that when they get input from those sensors, to cut off the engines because the spacecraft has landed. But it turns out there's some noise or false signals by the sensors that are generated when the landing legs are extended. They're extended before it actually gets down to the surface. But that wasn't in the software requirements. The software, now maybe we don't know why they didn't put it in the software requirements. It may have just been a slip up. May have also been that the software wasn't supposed to be operating at that time anyway. But the software engineers decided to start early in order to even out the load on the processor. So in the end, the software thought the spacecraft had landed, shut down the descent engines while it was still 40 meters above the surface, and we lost the spacecraft. Again, everything worked the way it was supposed to work. The requirements, the interactions were wrong. Here's another one. This is a Warsaw. In Warsaw, it was an Airbus A320. The software protects against activating the reverse thrusters. Those are, when you want to stop the plane, you can probably feel it when you're landing on a plane. What they do is change the direction of the thrust. Instead of pushing the plane forward, they make engines are changed so it pushes against the way a direction that it's traveling, and therefore slows down the aircraft when you land. So it turns out it's very unsafe, very dangerous if those reverse thrusters go on when the plane is airborne. And there had been an accident like this before, and they blamed the pilots. Nobody knows exactly why it went on, but they decided to protect against this in the software. But it turns out then the software has to know when the plane is landed in order to allow the reverse thrusters to actually be used. And it turned out there was a lot of rain and there were other factors. I don't want to go into the details, but the software didn't think that the plane had landed. So the pilots couldn't activate the reverse thrusters and ran off the end of the runway into a small hill. Again, the pilots did the right thing. The software did exactly what it was designed to do. This was, again, a requirements problem. Here's one more that you've probably heard of. This was the Boeing lithium-ion battery fires. The plane had been certified based on models predicting that the 787, the Dreamliner battery thermal problems would occur once in 10 million flight hours, but 2 batteries overheated in just 2 weeks in 2013. Now, these accidents are always very complicated, but here's just one factor that I think will interest you. And this will happen in it actually happened in Boston. There's a module that monitors for smoke in the battery bay, because getting smoke into a plane is really bad, especially into the cockpit, as you can imagine, because the pilots now can't breathe and fly the plane. So there's a module that monitors for any smoke, and if it detects smoke, it activates some fans and ducts to exhaust the smoke overboard and not let it get into the cabin. Now there's another module that monitors for low battery voltage. And if there's low battery voltage, which could happen if there's a fire, it shut down various electronics. Unfortunately, some of the electronics that shut down were the ventilation that was outboarding the exhaust. So smoke couldn't be redirected outside the cabin. All the software requirements were satisfied, the requirements were unsafe. And here's just one more. This one I like because I live part-time in Seattle, and we have a lot of ferries because there's water everywhere in Seattle. So we have a lot of car ferries. Now, there was a local rental company was having a lot of its cars stolen, not by being hot-wired, but by having thieves come up with a tow truck and just tow away these new cars. So they installed a security device to prevent the theft by disabling the cars if the car moved when the engine was stopped, which seemed like a good idea to them. But remember, there's all these ferries. And all these cars got on the ferry and stopped their engines. But when the ferry moved, the cars weren't running. And so this software disabled the cars. And when they got to port, it was a mess because they couldn't drive the ferries the cars off the ferry, and they were blocking out the other cars. And it was a mess. It wasn't certainly a safety problem, but it's the same kind of problem that we're having. There are 2 kinds of accidents here. There are component failure accidents that are caused by single or multiple component failures. Usually we assume some kind of random failure about it, and we understand those, and we do lots of redundancy and other things, and we know how to handle them. But these new kind of accidents, these component interaction accidents, arise in the interactions among the components, not necessarily failures of components. It's related to complexity or tight coupling in our system design, which leads to system design and system engineering errors. It's exacerbated. No components may have failed, and it's made worse by the introduction of computers and software. But the problem isn't a software problem or a computer problem. The problem is system design errors. And part of the problem arises because software allows almost unlimited complexity in our designs. So the point here is that software and safety and reliability are different properties. They are not the same. In the green circle, if you look at the green circle in the Venn diagram, those are the scenarios that involve failures of the system, where the system may be unreliable in area A, but not unsafe. There's some overlap. There's also the pink circle has the unsafe scenarios. There's overlap in area C, where it's unreliable and unsafe, and just about any technique handles those. But the problem is B, is that we're seeing now, where it's unsafe, but it's not unreliable. There's no failures. And that's the problem we need to solve now. We know how to deal with failures. That's not a problem. We need to be able to solve the problem of unsafe, but reliable. So let's look at software and more about the problem. The problem is really unlimited system complexity that software allows. We can no longer plan, understand, anticipate, and guard against all undesired system behavior. And as we all know, we can't exhaustively test the software and the system to get all the design errors out. Now, one of the things we need to recognize is, context determines whether software is safe or not. The Ariane 4 software was safe, but when it was reused in the Ariane 5, the spacecraft exploded. It led to the explosion of the spacecraft. This is always true. You cannot determine whether software is safe or not without looking at context. So, you know, a lot of people have all these mix up again, safety and reliability. And so there's a lot of people talk about now a SIL, safety integrity level. That's technically meaningless. It's assigned to the software without looking at what context it's going to be used for. Well, the software could be safe or unsafe. It's totally dependent on context. So SIL, or the safety integrity level, doesn't mean anything. And other people talk about level of rigor, or design assurance level is used in aircraft. Again, these have nothing to do with the problem. If you rigorously develop your software, but your requirements and your system requirements and your software requirements are unsafe, it doesn't matter how much rigor you use. And again, it's just not possible to look at software alone and determine whether it's safe or not. So here's a butter knife. Is that safe or is that unsafe? Well, it depends on how you use the butter knife. And it's the same thing with safety. Safety is always a system problem. It is not a component problem. You can't just look at one component of a system and determine whether the system will be safe or not. And just to repeat and stress this, the role of software in accidents almost always involves flawed requirements, either incomplete or wrong assumptions about the operation of the controlled system or the required operation of the computer, or unhandled control system states and environmental conditions. So in this diagram here, an autopilot produces some experts say produces some requirements that the software engineer implements, and the software engineer is basically designing the autopilot. The safety integrity level, the level of rigor, has absolutely nothing to do with the problem. It also is not going to help to worry about just whether the software engineer correctly implements the requirements in the design, because that's not the problem either. The problem is almost always in the requirements. So only trying to get the software correct or to make it reliable isn't going to make it safer under these conditions. And this is the reality that people seem to be ignoring. There's also, computers change the role of humans in systems. There's a typical assumption that operator error is the cause of most accidents and incidents. So what we should do is do something about the operator involved. Fire them, retrain them, whatever, or do something about operators in general. Marginalize them by putting in more automation, so we make this thing even more autonomous, or rigidify their work by creating more rules and procedures. And all this does is end up making the problem worse. This is an example of, this is a real accident report. It was American Airlines 757 crash in Cali, Colombia, when they were, and this is just typical. This is the kind of thing I see all the time. First of all, it's always the flight crew's problem. So the failure of the flight crew to revert to basic radio navigation at the time when the flight management system, that's the software assisted navigation, became confusing and demanded an excessive workload in a critical phase of flight. So what you see here is we blame the pilot before using confusing automation. The pilot didn't make the automation. Somebody created confusing automation, but that doesn't seem to be the problem. We aren't blaming that. It's the pilot's fault for using it. This is astoundingly nonsense. Fumbling for his recline button, Ted unwittingly instigates a disaster. Again, context and the environment in which a human works will determine their behavior. Here's another accident involving thrust reversers. This was a Tupolev aircraft in Moscow. It was landing in the Moscow airport. It made a soft touchdown. What that just means is it made the runway contact a little later than usual. Now, this was a little bit different. There was also a crosswind, which meant the weight on wheel switches didn't activate and the reverse thrust system, again, wouldn't deploy. In other words, the software didn't think the plane had landed, so it wouldn't let the pilots deploy the reverse thrusters. But this was a little bit different, because in this case, the pilots believed that they were going to deploy, like they always do, that the reverse thrusters were going to come on. So with the limited runway space, they quickly engaged high engine power in order to stop quicker. Instead, it accelerated the plane aircraft forwards, and eventually it collided with a highway embankment. In complex systems, and this is something that software engineers probably don't want to hear, but need to hear, human and technical considerations cannot be isolated. We can't ignore the humans who are using this software. So what we normally do now is we divide things up. The human factors experts concentrate on the screen out. So the design of the screen, the training of the person, the controls that they're using. And on the other hand, on the other side, the hardware software engineers concentrate on the screen in. They don't think about what the humans, at least that don't do it enough. I don't want to blame everyone for not doing this, but unfortunately, it's pretty universal. And they look at the screen in, and nobody is looking at the system as an integrated whole. So we're getting all kinds of new kinds of errors, mode confusion, which means that the software confuses the pilot about what mode the plane is in, and then the pilot does the wrong thing, crashes, and it gets blamed. Situational awareness errors, very inconsistent behavior by the software, which confuses pilots. If we want to solve this problem, we need to be able to work with and include the users, the operators, and human factors in solving the problem. So This is the new systems view. What I told you first was the old view of and standard view of operator error. Here's the new systems view of operator error. Operator is a symptom. It's never a cause. All behavior is affected by the context in which that behavior occurs. So we're changing the role of the operators in these software-intensive systems. And the errors, it's also changing the errors that they make, but we are basically designing systems in which operator error, say pilot error, is inevitable, and then we blame the accidents on the operators rather than on the designers. So to do something about operator error, we need to look at the system in which people work. The bottom line is the human error is a symptom of a system that needs to be redesigned. So here's the problem we're trying to solve. And I said I've described the problem. We need models and tools that can handle hardware and hardware failures, not just software, can handle software, but particularly software requirements, errors and flaws, human factors, interactions among the system components, system design errors, management, regulation, policy, environmental factors, all those things that engineers call the unknown unknown, and the interactions among all these things. And if we're going to solve the problems with safety, we're going to have to develop tools and other things that handle all of these things, not just look at software. So again, I remember the little birds. We are too often now feeding worms into the baby. Again, people mean well, they're trying to solve the problem. They're just don't understand that the problem has changed that they're trying to solve. So we need new tools for the new problems. So that's the first part of my talk. What's the problem? And now I'm going to suggest an approach. I'm not going to go into any of the details, but I'm going to suggest a new approach that will allow us to make progress and is allowing us to make progress. And the problem basically that we're trying to deal with is complexity, right? Now, there's three ways that humans and engineers have found to cope with complexity. One of them is analytic decomposition. I'll show you what that means. Another is statistics, and the third is systems theory, which you may not have heard of. So let's look at analytic decomposition. This is the same, we've all been taught to do this, divide and conquer. If you have a complex system, you divide it into separate parts, and then you work and analyze the parts separately. If it's behavior, it separated into events over time. You've all heard about the chain of events supposedly leading to an accident. And then we analyze and examine the pieces separately and combine the results. And it sounds good. I mean, we've been doing this since the scientific revolution, back in the 1600s, Descartes and others. And it's been tremendously successful. The problem is that it assumes that the separation doesn't distort the phenomenon. And in the systems we've dealt with so far in the past, that's been true. And so there are these assumptions that unfortunately aren't true for our software intensive systems, that each component or subsystems operates independently, that they act the same when you look at them singly as when you look at their interactions as a whole. The components are subject to feedback loops, nonlinear interactions, and so on, and that they can be examined pairwise, so we can put these things back together again. The bottom line is these assumptions are no longer true and are tightly coupled, software-intensive, highly automated, connected engineered system. And we need a new theoretical basis. And I believe that new theoretical basis that can be used, and we're showing that to be true, is something called system theory, which unfortunately is not new, but is just not taught in most of our engineering schools. So if we look at this, and we look at the sort of cartoon, it's not a real graph, but if we have on the y-axis the degree of randomness, on the x the degree of coupling, there comes a point, at a certain point of randomness, something called in system theory called unorganized complexity. If the randomness is high enough, you can use statistics, but that's not true for software. Software is not random in its behavior. If the degree of randomness is less, but the degree of coupling is limited, then we have this area called organized simplicity, and that's where we can use analytic decomposition. The problem today is that most of the systems we're trying to build have what's called organized complexity. They're too complex for analytic decomposition, although computer scientists and formal methods people are not going to give up trying, and they're not random enough to use statistics on. So we need a paradigm change. And here's my definition of the paradigm change that I think we need. Instead of treating safety as a failure problem, which we've done in the past, we need to treat safety as a control problem. So I'll explain what I mean by that. Systems theory in general was developed for systems that are too complex for complete analysis. If you separate them into subsystems, it distorts the results. The most important properties are emergent. They emerge when the components interact, and I'll explain a little more about that. But they're also too organized for statistics. Systems theory is not new. Its first use on the ICBM systems in the 1950s and 60s was actually developed in biology and in engineering in the 1940s. And it was created to provide a more powerful way to deal with the kinds of complexity that we started seeing around the middle of the last century. And it focuses on systems taken as a whole, not on the parts taken separately. And again, I said I'd talk about these emergent properties. There are some properties that can only be treated adequately in their entirety, where you take account of all the even social and technical aspects. And you've probably heard this phrase, and this phrase comes out of systems theory. The whole is greater than the sum of the parts. That explains emergent properties. Emergent properties arise, they're not in just the sum of the parts, they arise from the interactions and the relationships among the parts of the system, how they interact and fit together. So here's maybe a hopefully clear picture of this whole thing. We have this process and the components interact in direct and indirect ways. And as they interact, they create these emergent properties. They arise from the complex interactions, which is exactly what we need to deal with safety. And in fact, I contend that safety and security are emergent properties, both of them. And why we're having so much trouble, especially with safety, by trying to use analytic decomposition. If I show you a valve and I tell you this valve is going to be used in this autonomous car, will the car be safe? And you're going to look at me like I'm crazy. Well, how? I don't know. How are you using the valve? What's it got to do with the whole design of the car? Why, what are the hazards related to it? You can't do it just by looking at the components. You have to look at the system as a whole. So how do we solve this problem? Okay, so here's the solution. We need to control these emergent properties, enforce constraints on the interactions. Actually, on two things. We have to enforce constraints on the individual component behavior and also on the component interactions. So we still need to worry about individual component behavior and failures, but we also have to be able to enforce constraints on the interactions among the components. So what do I mean by safety constraints? Well, here's examples. Power must never be on when the access door to the power supply is open. 2 aircraft or automobiles must not violate minimum separation. Aircraft must maintain sufficient lift to remain airborne. The integrity of the hull must be maintained on a submarine. Remember, these were, I told you there were goals of the system and there were constraints on how those goals can be achieved. So toxic chemicals and radiation must not be released from the plant. Workers must not be exposed to workplace hazards. The public health system must prevent the exposure of the public to contaminated water and food products and pandemic viruses, I should have probably add today. Pressure in an offshore well must be controlled. These are the high-level functional hazard-related requirements, safety and security requirements that need to be addressed during design. So what we need to do is be able to identify the requirements and make sure that they are translated into requirements on the components. So is this, this isn't quite, if you know, when you think about an example here, you're going to see this isn't such a strange idea. Air traffic control is exactly this idea. There are certain constraints that you want to impose on air traffic, like you don't want 2 planes headed toward each other on the same trajectory. That's the safety constraint. So what do? We don't allow all the planes to just go whatever way they want and then hope the pilots are going to maintain their own separation. We put in a control system, this air traffic control, which controls the trajectories of the planes and keeps them out from each other. It also, by the way, controls other emergent properties like throughput. So each airline could try and implement their optimal route. The problem is then they're all going to be end up in Charles de Gaulle or in Chicago or LAX or in Japan or wherever, the main airport. They're all going to be there at 8 a.m. or at 5 p.m. And no one then will end up getting their optimized, usually their optimized route or throughput. So the air traffic controller optimizes throughput as a whole. So each airline may not get optimized, but the throughput overall is optimized. That's the idea of system theory. So what we do is, so how does this relate to what you're doing, which is controlling software? I simplified that earlier model I had. And here I just included a controller at the top and a controlled process at the bottom. And the controller issues control actions via actuators on the controlled process and gets feedback via sensors. Now, every controller, whether human or software, has to have a model of the process it's controlling, the model of the current state of the process. It also has some kind of control algorithm, although with humans, it's more a decision-making process. Software and human-related accidents often occur when this process model is incorrect. That's a much more better explanation of why accidents occur and the contribution of software or humans to accidents than saying the software failed. I mean, it didn't fail. It did exactly what it was told to do. This captures software errors, human errors, flawed requirements. Let's look at an example here. This was the Mars Climate Orbiter. The hazard is landing on the planet with too much force. What happened was the spacecraft software got some feedback that from the landing leg sensor feedback said, it's landed, and that turned out to be false. But the process model for the software, and you're going to say, I don't have a process model. You do, you just don't call it that. It may only be a few variables, but you have to know something about the state of the thing you're controlling. And that process model in this case said the spacecraft is landed, so the spacecraft software issued a command to turn off the descent engines. And we could explain all of those accidents that I talked about in this way. And it's not only an explanation, we can use this actually to identify these problems before they happen and prevent them. So we have some control actions. This is the type of analysis that needs to be done. There are 4 types of unsafe control actions. And then what we do is use analysis methods to identify potential unsafe control actions, identify why they might be given. Why would the software not allow the reverse thrusters to be whatever. I don't know why I'm having a senior moment here. Identify why those unsafe control actions might be given, and if safe ones are provided, why wouldn't they follow, which really handles the hardware failure problem. So, but this requires us, one of the good things about this, it actually provides a model to do analysis on. This is a standard kind of block diagram, or this happens to be for a spacecraft. You're not going to be able to tell that, but this is for a spacecraft. It's the standard kind of model. This has hardware in it too, but all the object-oriented models, SysML, UML, all those all look like somewhat this kind of a block diagram. System theory and the way we do handle these problems instead use a functional model. This is this control model. So here's the same system, but using a different model, where this shows there's a ground station. The ground station sends commands up to the spacecraft. The spacecraft has software, attitude and orbit control system software on it, and issues commands to the reaction control system, which is actually the physical systems that control the attitude of this spacecraft. There's also some science instruments, and the ground station can send up commands to the ground station. Now, we do the analysis. You can do the analysis on this model. So you can look at, and what can you get out of it? You can look at software-hardware interactions and ones that may be unsafe or dysfunctional. Human automation interactions, human hardware interactions, and we can now even look at human-human interactions. So we can look at the social parts of the systems and the components. So I haven't got time. I'm not going to show you the actual analysis, unfortunately, but I'll tell you where you can learn more about it later. But I do want to mention security. What this does is allow an integrated approach to safety and security. The analysis for safety and security are going to be identical. Now, why is this true? Well, because this is very different than we do. Not only is it different than we do for safety, this is really different than what we do today for security. Both safety and security are concerned with losses, intentional or unintentional losses. We're looking here at a problem. We have focused in security almost all on information protection. But the problem isn't protecting information. It's assuring the mission or the goals of the system are achieved, or the constraints are achieved. So someone who goes in and tampers with the brakes on a car aren't worrying about stealing the Social Security number, the driver. They are looking at the mission or the goals of the system. And so what we want to do is ensure not that information is protected, but that critical functions and services are maintained. So this new paradigm for safety works for security too. We have to add a few new causes. The rest of the process is exactly the same. It's basically a top-down system engineering approach to designing safety and security into systems from the very beginning. So here's an example of Stuxnet. Hopefully you all know what Stuxnet. That was the Iranian worm. The loss was damage to the reactor, in this case, the centrifuges. The hazard or vulnerability were that the centrifuges were damaged by spinning too fast, and we slowed down the Iranian nuclear reactor program because they were continually running out of centrifuges and destroying their centrifuges. So the constraint to be enforced is the centrifuges must never spin above the maximum speed. The hazardous control action is issuing an increased speed command when it's already spinning at the maximum speed. There's one potential causal scenario is, again, an incorrect process model. And in fact, this is what happened. The worm made the software think that it was spinning at less than the maximum speed, so they kept adding an increased speed and increased speed until the things were worn out. This could be inadvertent or deliberate. I mean, it doesn't necessarily have to be a security problem. This could be just an error. And the potential controls are interesting and are the same. We can have a mechanical limiter, some kind of interlock that doesn't allow the centrifuges to physically just doesn't allow them to spin it faster than a safe speed. We could have an analog RPM gauge instead of depending on the software. But the focus here is on preventing the hazardous state, not keeping intruders out. We've been trying to keep intruders out for many years. I'm sure you all have had all of your stuff stolen like I have off the web. I get letters all the time telling me that all of my information has been stolen. We can't keep people out, period. I had a graduate student, a master's student who's actually in computer science, and we were doing some security, a master's thesis at MIT. And we needed some information from a large aerospace company. It was a security for aircraft. And we needed some information. We had asked them for it, and they were very slow about providing it. And he was anxious to graduate and get done. And so he came in my office one day and he says, well, they won't send it. I said, well, we got to keep trying. And he said, well, what if I just break in and get the information? And very casually, he said, I can do that. And I said, no, don't do that. And he got a little lecture about ethics and other things, which I think he didn't really understand. It went over his head. But the point is that we can't keep people out. It's not a viable solution to the problem. And all we're doing is spending a lot of money in this sort of warfare game, tactical game between the good guys and the bad guys. So there is something that I come up with called STAMP, System Theoretic Accident Model and Process. It's just a new, more powerful accident causality model. It's based on systems theory, not reliability theory. It defines accidents and losses as a dynamic control problem versus a failure problem. It applies to very complex systems. It includes all the scenarios from traditional hazard analysis of failure events, plus the component and interaction accidents, software and system design errors, requirements problems, human errors, and so on, the entire socio-technical system. So what can we do with this? Well, this is just a model. It's a causality model, a formal model of how accidents occur. But on that, we can build all kinds of tools. And we've got accident analysis tools used in accident investigation. There's hazard analysis tools. One thing, the most popular is called STPA, System Theoretic Process Analysis, which identifies the scenarios so that you can build the system and eliminate them from the very beginning of development. Model-based system engineering techniques, which use a different kind of model. This is one of the biggest problems I have is software engineers say, well, we only want to use object-oriented models. Well, you can't do this with an object-oriented model. I'm sorry, you need a functional model. Like I showed you. And if you're insisting on doing that, then you're not going to be able to solve the problem, period. We can do organizational and cultural risk analysis. We can identify leading indicators when risk is increasing during operations. We can do the security analysis, and then we can put these tools together and get various new kinds of processes like system engineering process, risk management, organizational design, new ways of certifying and acquiring complex systems, and so on. So I'm just going to finish up by talking about, does this work? All right, how's it being used? Well, turns out STPA has been or is being used in a very large, in virtually every industry that has any safety related problems at all. Automobiles, I would estimate at least 80% of the auto companies, especially autonomous auto companies, are using STPA today. There's extensive use in aircraft, UAVs, defense systems, air traffic control less, spacecraft less, medical devices, and some of these others less and less. These people are not into doing something new. There are new international standards for STPA in automobiles, or they're in the development for autos and for aircraft. Does it work? So it may be used, and hundreds of people are now using this. And one of the reasons that, I always think it's very interesting when software engineers or system engineers in academia complain about nobody wants that technology transfer is difficult. Technology transfer is not difficult. I have never had a problem with technology transfer because I start from the problem that people have, not the problem that I already have a solution for, and then try and convince them this will solve the problem they have. I also make all my students in their theses, dissertations, etc., even in some of the classes, they have to do them on real systems. You don't get to make up a toy system. Anything works on a toy system, especially if you get to ignore all the ugly, messy parts of the problem. If you can show people that, first of all, start from a problem that they really need to solve, and you can show them it will solve them on their systems, there's just really no problem in getting people to adopt stuff. I mean, sometimes I have companies that pay just to have somebody sit in my lab and see where we are because they don't want to wait what we're doing because they don't want to wait till we publish it. But does this stuff really work, or am I just a good salesperson? Well, there have been hundreds of evaluations now and comparisons with the traditional approaches that are used now. Walt Tishy, if you're listening, you will be happy. I am doing these kinds of evaluations and analyses on real systems. There have been, as I say, hundreds of controlled scientific and empirical. By empirical, I mean in industry, what happens is companies just do a parallel, use our techniques and then use their standard techniques and then compare the difference. Everyone has shown that STPA is better. It identifies more critical requirements or design flaws. What surprised me the most was that all the ones that measured showed that it required orders of magnitude fewer resources than the traditional techniques. And this, I didn't understand at first, because if something's more powerful, if it finds all the old stuff and then plus it's got to be, you know, it seems intuitive, it's got to be more expensive. But it turns out it's not, it's much cheaper because you're tackling the problem in a totally different way. We've also had lots of instances where we found accidents before they occurred. Sometimes these were on defense systems where we did STPA, or the engineers did STPA. They found scenarios for accidents, but management said, oh, we don't want to bother fixing it. It's never going to happen. And then so then they release the system, put it into operation, and it happens. So it's finding real accidents. And in fact, in some cases, in one controlled experiment, they actually gave the design of a real system, and they didn't tell the people, but they had all these people do different analysis techniques, and they asked us to do STPA on it. And it was a design of a nuclear power plant shutdown system. And so we just did it. And afterwards, they told us there had been an accident, a real accident in this nuclear power plant, in this design. And the STPA, and it turned out STPA was the only one that found it. What about return on investment? Well, the estimates are only beginning, but one large defense industry contractor claims they're seeing 15 to 20% return on investment when using STPA versus the traditional techniques. For example, on $1 billion project, they estimate they saved $127 million. And why did they save money? Well, because they found all the problems early. The big problem, you all know, you're software engineers, you know, it's astoundingly expensive to change things later in the process. After you've already designed the thing, now you're testing it, and all of a sudden you find a big flaw. Going back and changing that is really expensive, and that's eliminated. So what do we need to do? I'm actually finishing. We need to develop and use different approaches to match the world of engineering today and the problems today, not what the problems of yesterday or the problems that we'd like to think that the people have. We need to solve the problems people actually have. I didn't spend a lot of time on this. We need to consider the entire socio-technical system. And we need to focus on building safety and security, and rather than assuring or measuring it after the design is complete. There's all this effort now on assuring safety, software safety. It is impossible. I don't know why people are trying to do this. It cannot be done. You cannot assure safety in after the fact. If it's not there, you're not going to prove it's there. And if you find out at the end it isn't there, you're not going to be able to have the money or the time or the ability to make changes. So what happens is people make proofs that look like they're right, and they've argued themselves into thinking it's correct. And every one of them I've looked at, and I've looked at lots of them, dozens, and they're all just incorrect. The argument is incorrect. They're using what's called confirmation bias. They focus on trying to show it's safe rather than trying to show it's unsafe. And bottom line, we need to start from the problem that's actually there, not start from an old solution for a different problem. And in other words, avoid feeding worms to the baby. So I didn't give you any details. I didn't show you examples of the analysis or anything. I want to encourage more people to do this kind of thing. Stop just doing all the old stuff that everybody's all done for the last 40, 50 years in computer science and saying somehow this is going to solve the safety problem. I wanted to describe the safety problem is different. And we're not going to solve it by just recycling old techniques. We need to start from the problem itself. If you want more information, there's a website, lots of papers, presentations from conferences, and so on. I have a book, Engineering a Safer World. You can get a free download. You probably can't write all this down right now, but if you, I hear someone, I'm finishing. If you want a free, if you just Google Engineering a Safer World, the free copy comes up very high on the list first. There's an SDPA handbook that's had something like, we've had it up on the website for 24 months. It's had more than 65,000 downloads. It's written in Japanese, Chinese, and Korean versions. Engineers just volunteered to change it into their language. So we've got those up on the website too. We've got a handbook for something called CAST, which is an accident investigation thing. And I just want to mention one thing from July 20th to October 7th, we're having a virtual workshop on this stuff. There'll be tutorials, there'll be industry presentations of what people are doing in industry, research presentations, and so on. And you can find out more information on this website. So, Greg, were you trying to,
No, that was, I was unmuting in anticipation of getting to the question period, but I was not trying to stop you. So.
Okay, well, I'm only 5 minutes over. So
you're doing great.
Time for questions. So.
Yep, you did. I should probably explain to people, since this is the first question time we got to, that for those of you who aren't on Clouder, people on Clouder have been asking questions, and people can upvote those questions. And I have that question list here. And in this session and others, the session chair will ask the questions of the speaker. There's a 10-second or so time lag between what's happening on Clouder and what you're seeing on YouTube, and that makes it better for me to ask the questions. And also Slido allows the votes, and we can't bring the whole audience into the Zoom room to ask questions. So the questions are here, and people have been upvoting them, and I think I will start from the top.
Yeah, it's a little weird doing this virtually.
It is, yes.
Yeah, and I can't see anyone, and whether they actually are all asleep, or you know, reading their program or something. Or
well, they've been asking questions. We can tell. I can tell you that, and I'm about to ask them. And, yeah, the only thing you can't do is ask for a clarification of a question very easily. Anyway, the top question. Thanks for the great talk. How do you envision the widespread use of machine learning will impact safely? They say can negatively impact safety. Do you foresee it having a positive impact?
Positive impact?
Let me restate it. Thanks for the great talk. How do you envision the widespread use of machine learning can negatively impact safety? Or do you foresee it having a positive impact, machine learning, on safety?
Okay, but the widespread use of what? That was
right. Machine learning.
The what?
Machine learning. And machine learning?
Oh, machine learning.
Yep, sorry.
Oh, yeah, you know, who knows? I don't, we're trying to work on that because people keep coming to us with money and ask us to work on it. We're making some progress. We're not ready to announce it yet. But machine learning is a real problem. And because if you don't know what the thing's going to do beforehand, how in the world can you ensure it's safe? And, you know, we've always had monitors and wrappers and stuff, and they don't work. And they haven't worked in 40 years, so they're not going to work now. So I'm not sure that that's the solution. And so unfortunately, I don't have a solution for that problem. But we may actually in a few months. Just not ready to announce it yet.
Okay. Can you give an example of how security and reliability conflict?
How safety and reliability?
Yeah, I think they probably mean safety and reliability.
Okay, yeah, I was wondering what the, okay. So, all right. So that torpedo, let's go back to the torpedo. It was very safe.
Oops.
It just turned itself off and lay there. But it wasn't reliable at all. So safety and reliability are really different things. Reliability is, does it satisfy its requirements? Safety is, are the requirements safe? Will the requirements lead to the thing being to lead to a hazard in the system? Reliability has nothing to do with hazards. Reliability is just, does it satisfy its requirements?
Okay. Here we go. Can we separate software from its implementation? This seems to be what is implied when you say it isn't software that is unsafe, but it's implementation errors.
Okay, now it's not implementation errors. The implementation errors almost, I have never found a accident of hundreds of them where it was just an implementation error, design error. It was always, it looked like it was an implementation error, and you go back and it was because the requirements were wrong. And all those examples were requirement problems. We can probably explain it, but it would take me a while to explain why I think this is true. But from all the evidence and the empirical evidence and all the accidents, we're going to have to work on the requirements. Safe software by itself doesn't do anything. It just sort of sits there. It's only when it has some impact on some physical device and that leads to a hazard that we have a problem. There's actually a lot of empirical data. Robin Lutz did a study of spacecraft and found that virtually all of them, there were implementation errors, but they weren't safety critical. That the safety critical ones were the requirements problems.
Okay. Do you have any pointers on how to account for unforeseen emergent behaviors? Any default rules of thumb that one can follow?
Okay. Unforeseen just means emergent. And what actually engineers, when they learn SDPA, one of the most common things they say, oh, I can find the unknown unknowns. What it does is it forces you to look at what could go wrong. Instead of trying to look at what goes right, you look at what could go wrong. How could a hazard arise? And that's when you find sort of unforeseen if you're not looking at these things. So the problem is our systems are just too complex for us to understand all the interactions, all of the states it can get into today. It's just not going to happen, especially when you put humans in and hardware and all these other things in the environment. So the goal of hazard analysis is to foresee these things so that they're not unforeseen. The goal is to foresee them, not to prove you've already got it right, but to identify the things that could happen that could lead to a hazard, and then either eliminate those from your design, or try, if you can't eliminate the hazard, then you try and control it or mitigate it if it occurs.
Okay. How has or will the diminishment of adversarial regulatory review in countries like the US affect safety?
Adversarial
review and regulatory is in parentheses. How has the diminishment or the reduction of adversarial review regulatory review in countries like the US affects safety.
Okay. I'm not sure I understand the question, so I'll try answering a question that I think I may be asked. Every agency in each industry has a very different approach to regulation. Probably the one that we're most familiar with, most of the people listening, is the aviation regulation. Although there are regulations, we regulate also nuclear power plants, we regulate medical devices, and we don't regulate cars very much. So it's very different. So in nuclear, they tend to believe in the probabilistic reliability approach. And it doesn't work, especially for these kinds of software intensive systems. So I can't say the name of it, but there was an unmanned aerial vehicle that had been certified as a basis of 10 to the minus 12 probability of a crash per flight, I think it was, or for a flight hour. It doesn't matter because that number is so small. It translated there wouldn't be an accident for 500,000 years. It's already crashed 5 times in the first year of operation. That's not going to work. We cannot, probabilistic analyses aren't going to work if you have software in these things. They only work if they're pure hardware, and it's old hardware where you have already have a lot of historical information. Not going to work. The certification of aircraft, civil aviation, commercial aircraft, of course, has now come to been a lot of talk about this since the 737 MAX accidents, and a lot of the problems were not technical, although there are technical problems, but they were regulatory problems. The FAA ceded control over certification to Boeing, and that was a mistake. There are also problems in the way it's certified. They take a failure approach. So they look at component failures and they do analytic reduction, and it's not going to work. There are right now lots of new standards being written for SDPA and for other approaches. And we need to, as a community, software engineers, the community needs to develop better ways of doing this. This DL 178B or C, which probably you're familiar with, is just a design assurance level, which basically just says, and level of rigor, basically says, well, just do a good job developing the software and it'll be okay. Implementing the software, and basically most of it's testing the software. Well, that's not going to do it. The problems are in the requirements. So that's not going to solve our problem at all. It makes it look like we're solving the problem, but DL 178C, and those in this industry listening will know what I'm talking about, has actually nothing to do with safety. There is not the word hazard anywhere in it. It is not a safety standard. It's a reliability standard.
Okay, thank you. Well, we did have our first, it's not a safety failure, but failure in that the questions, there were about 14 questions there and they disappeared. But someone has, so I'm going to, another question has come in and maybe some people will will repost the questions they had. So I'll begin with, I see two now. So they're coming back in. Do you think that safety requirements are not the same in different industries? And how do you think this could impact the process?
Well, the hazards are different in different industries. So the requirements can't be the same. They've got to be different. You know, if a hazard is, the hazard for nuclear power plant is a meltdown, it's a release of, or a release of radioactive material or radioactive toxins. That's not the problem in the auto industry. So if the hazard's different, the requirements are obviously going to be different. Again, you've got to look at the system. The hazards are in the hardware, in the system. They're not in the software. So you can't just look at the software. And I know people don't want to hear that, because the solution, the nice solution would be just to be able to have the safety integrity level or whatever, the software, and just say, oh, well, we'll just make the software right. The software may be right or wrong with respect to implementing the requirements, but that doesn't mean it's safe or unsafe.
Okay. Is it reasonable to consider the act of requirement specification, especially their interaction and emergent properties, a programming task?
Could you repeat that?
I can, yeah. Is it reasonable to consider the act of requirement specification, especially their interaction and emergent properties, a programming task?
As a programming problem?
Yeah, let me say it a different way. Is it reasonable to consider the act of requirement specification as a programming task? And then in parentheses, there was especially their interaction and emergent properties.
No, it's not a programming problem. It's an engineering problem. That's very different. The requirements come from the physical engineered system. It's not a programming problem. A programming, I know that that's what people want to do. They want to be able to use formal methods to show consistency between the requirements and the software, and they take software as a formal, formal language, and the requirements is a formal language, and will show the consistency between them. And you can do that, but it'll have zero impact on safety, because the problem, it isn't a programming problem, it's an analysis of problem, at a system analysis problem, and that's what SDPA does. SDPA actually is not hard. If I had time, I would have showed you, you can learn it in a day easily, and it's not hard to do at all. It just requires thinking differently about the problem. But it's not a programming problem. It's an engineering analysis problem.
Okay. And some of these questions are coming back. We should build tools that work for any system, but the pressure for publishing can push people to build toy tools. How can we reward the engineering work?
Okay, so one more time.
Sure.
It's not coming through that clear.
I know this is different. We should build tools that work for any system, but the pressure for publishing can push people to build toy tools. How can we reward the engineering work?
So the publishing, that's an interesting question. We have to stop publishing things that are just not focused on real problems, that are just copying what everyone else has done before. And there's no problem. When I was in the early 80s, when I was still just learning about this problem, I wrote the stupid paper published in a very top journal about Petri nets and how you could use Petri nets for hazard analysis. Why? Because that's what I was taught when I was in graduate school. It's a lovely model. I love Petri nets. They're fun to do. So I said we would use them for hazard analysis. That was 40 years ago. They've never been used. They can't be used for that. No one will ever use it for that. But this is one of my most highly cited papers. People still have PetriNet papers as at conferences, and they keep citing this paper and saying and improving on this stupid technique that I never should have published to begin with. And it gets published in conferences and in journals, but nobody ever uses these things. So it just depends. If your goal is just to, I understand. I was assistant professor at one point in my life too, and I published stuff that was very academic and would get me tenure, and then I stopped ever doing those things again. You need to decide, and I think we need to change our academia to, instead of rewarding people for doing things that aren't used, that can't be used, that don't work on any real problem, but are mathematically elegant and lovely and show off all our mathematical skills. And I love those things. I love formal methods. It was beautiful. I love logic, formal logic. It was lovely. It just doesn't solve any real problem. So there may be people who want to continue to do that, but we should have a way for people in academia to solve real problems. Force them, as Walt Tishy and other people have argued, and I argued for 40 years, force people to evaluate what they do, not just raise their proof by vigorous hand waving, say, yeah, this will solve the problem, but without any proof that it solves any real problem. Get real data, which I still do. Use it on real problems. There was, at one point, I remember I reviewed a software engineering program at a university that I just won't name it because it might give away the person. And it was really lovely. He was doing some very interesting software engineering things on how to write specification languages, how to make them readable, some really nice stuff. And he said, yeah, but I can't get it published because it's not formal methods. There's no elegant math behind it. So I'm going to have to change. And he did. And what happened, that was, 30 years ago. And what's happened is it's even gotten worse, that the top conferences, the top journals tend to be very focused on formal mathematical solutions to problems that aren't important, or mathematical solutions that aren't going to scale up. Look, in a car today, there are, in just the car you drive, there are 100 million lines of code. 100 million. The latest fanciest defense jet, like the F-35, probably, I don't know, probably maybe has 25 million. Your car has 100 million, and these autonomous vehicles maybe have 152 million, 200 million lines of software. You're not going to be using these fancy, elegant mathematical techniques on them that might scale up to maybe a few thousand lines of code if you have some PhDs and a lot of time. So this is something that the community has to reckon with. Do we want to continue to just show off what wonderful mathematicians we are? You shouldn't have asked me this question because I'm getting myself in horrible trouble now. I'm going to get all kinds of hate mail. But or are we going to start working on the really non-elegant, non-mathematical problems, but the really important problems that people need to solve? I realize that, in ICSE, there's probably lots of papers that are practical, but I stopped Ooh, I really gotta get myself in trouble. I stopped attending ICSI about 20 years ago. And reason was I looked at all the papers and none of them were solving any real problem that the people that I work with, the large companies that I worked with, really had. And they didn't seem to even understand what the problem was. They were instead reading journal papers and said, oh, well, I can do that better and improve that, instead of looking at what problems really needed to be solved. Ooh, I shouldn't have said all that.
No, that was great. That was a very, very good question and a good answer. We're coming to the end of our time. I think we're going to leave it on that question and answer.
Is that recorded clapping?
I believe it is. I've got to find out about that. But
I
I'm sure
don't
people
understand where
are
that's
clapping at
coming
home.
from.
I'm sure people are clapping at
Sounds
home.
like a soundtrack.
You know, this is kind of like being on a radio show, and you know you're talking, and you know there's an audience out there, but you can't see how they're reacting
Right.
or anything. Well, thank you everyone for coming to this session, and Nancy, thank you for a great talk. That was really, really wonderful, and for spending so long answering the questions.
Thank you for inviting me. It's really a pleasure and a compliment to be invited to speak to such a distinguished group.
Thank you so much. Folks, we'll see. There's another session in 10 minutes, so Zoom rooms. So, okay. Thank you.
All right. So I got myself in trouble in the last one. Walter Tishy, if he's watching, he'll be happy, but most
Okay, everybody, let me intervene and just say that we are going to stop the live streaming in about just a few seconds. Thanks, everybody.
Thank you. Okay.
I want to just remind people.
For a moment, I guess.
I want to remind people that in the third hour, please look at the program. There are some extra events to go to, like the poster sessions and some of the smaller interactive meeting rooms. They are all available. If you go to Sessions Live, you will see all the rooms there that are available, and you can check it out. If you're a poster presenter today, I believe there are some poster presenters. Please hang out in your poster, open up the video, and wait for people to join you. And we'll see you all in the next time band, which is the Indian time band.